Hello and welcome. These are the solutions to the Chapter 3 review. So determine and balance the reaction for sucrose, the combustion of sucrose, in the presence of excess oxygen. What are the coefficients in the reaction? So it'd be C12H22O11 plus O2 goes to CO2 plus water. We're going to have 11 waters, so that gives us 22 hydrogens. We're then going to have 12 CO2s. We're going to perhaps picture the 11 oxygens come from here, and then we have a 12 in front of the O2, so the coefficients should sum up to 13. So don't forget, when you're balancing out the O's, to count the 11 O's in sucrose plus the 12 times 2 in the oxygen, giving us a total of, whatever that is, 24 plus 11, that's 35 on the reactant side. Then we get 12 times 2 plus 11, so that's also 35 on the reactant side, on the product side. Number 2, calcium is the most abundant metal in the human body. A typical human body contains about 121 grams of calcium. How many atoms of calcium are present in 121 grams of calcium? And so the number of Ca atoms would be equal to the 121 grams of calcium. Use the molar mass, 40.08 grams of calcium per mole of calcium. 1 mole of calcium would contain an Avogadro's number of calcium atoms, 6.022 times 10 to the 23 calcium atoms. This would be 121 divided by 40.08 times Avogadro's number. Works out to 1.8 times 10 to the 24. Answer B. A 3.82 gram sample of magnesium nitride reacts with 7.73 grams of water. The yield of MgO is 7.73 grams. What is the percent yield? Okay, now a lot of times in these problems you think there's some sort of a trick. Maybe you think I take these two masses, add them together, and take this mass. No, there's the only thing you need to remember here is you have to figure out the limiting reactant versus the excess reactant. So you have to identify that limiting reactant, the one that's completely consumed by the reaction. We're going to ultimately be calculating the percent yield of MgO. So why don't we calculate 2 times the number of grams of MgO that can be produced if we consume all of each one of the reactants. So let's start with 3.82 grams of Mg3N2 versus if we take and figure out how many grams of product we can make of the MgO with the consumption of all of the water. And to see which one makes more or less. And so we're going to have to calculate some molar masses. So magnesium's 24.30. So that's times 3 plus 14.01 times 2. That's 100.9 grams of Mg3N for 1 mole of that. So 1 mole of Mg3N2 is 100.9 grams. When 1 mole of this reacts, we produce 3 moles of MgO. We're going to need the mass of MgO, so we're going to go to 1 mole of MgO. It has a molar mass of 24.30 plus 16.00, so that's 40.30. Okay, so what we're doing is figuring out how many grams of MgO could be produced by the consumption of all the Mg3N2. And because the percent yield, we're going to have to divide this by that theoretical maximum yield. And we do the same thing with water, except it's 18.02 grams per mole of water. We got to look at the coefficient for water. It's 3 moles of water that react, produce 3 moles of MgO. And then 1 mole of MgO still weighs 40.30 grams. Okay, so I'm going to do the arithmetic. 3.82 divide by 100.9 times 3 times 40.30. That works out to be 4.58 grams. And then when I do the arithmetic with consuming all the water, 7.73 divided by 18.02 times 3 divided by 3 times 40.30 works out to 17 4.3 grams. Okay, so if I consume all the water, I'd make 17 grams of product, but I'd run out of the Mg3N2 once I hit 4.58 grams. So the Mg3N2s are a limiting reactant in this problem. Water will be left over, but we're not asked about the excess. We're not going to worry about that. So we make 4.58 grams. So my percent yield should be equal to the 3.60 grams produced divided by the 4.58 grams theoretically that we should have gotten times 100%. So 3.6 divided by 4.85 times 100, 74.2%. I don't see that choice available. Let me double check my arithmetic. 24.3 times 3 plus 14.02 times 2. So that was right. 3.82 divided by 100.9 times 3 times 40.3. So 4.58. So that's still right. 3.6 divided by 4.58 again, 78.6. I guess I just calculated it wrong the first time when I did this step. But anyways, that does work out to be answer B. Okay. Number 4, what does an empirical formula always indicate? And choices are which atoms are attached to which in a molecule. That has no relationship. How many of each atom are in a molecule? It doesn't relate to that. That's the molecular formula. The simplest whole number ratios of the elements in a compound, that is what the empirical formula indicates. The isotopes of each element in a compound, there's no relation there. That's just nonsense. The geometry of a molecule, that's nonsense as well. So the answer is C. Moving on to number 5, which represents the reaction between sodium and fluorine. So remember, sodium is sodium metal. Fluorine exists as F2 gas. And so then this would be the reaction to produce the ionic compound NaF. So it's looking like reaction B, but B is not balanced correctly, so perhaps C looks like a better reaction. C would be the right answer. What's wrong with D is the wrong formula, like A is the wrong formula as well for sodium fluoride. And then E is wrong because it's not balanced correctly, so the answer is C. Percent carbon in cobalt-3 carbonate. And so we're just calculating cobalt's mass is 58.93 AMU. There's 2 of those. Oh, that's not asking the percent cobalt, it's asking the percent carbon. So the percent C would be equal to number of C atoms. So there's 3 carbon atoms, 12.01 AMU for each of those, and then the overall atomic weight will be 58.93 times 2 plus 12.01 plus 16 times 3 for the carbonate, that quantity times 3. So that should be 297.89 times, of course, 100%. So 3 times 12.01 divided by 297.89 works out to about 12.1%. So 12.10%. How many nitrogen atoms are in 4.72 grams of magnesium nitrate? And so number of N atoms, let me save some space. Number of N atoms equals the 4.72 grams times, we need the molar mass, so 24.3 plus 14.01 times 2 plus 16 times 6, so that's 148.3. That's per mole of MgNO3 and then 1 mole of MgNO3 contains an Avogadro's number of that unit. And then 1 MgNO3 contains 2 N atoms. So 4.72 grams to moles, divided by 148.3 to get there. So 0.0318 moles times Avogadro's number means we have 1.92 times 10 to the 22 units of magnesium nitrate, and then each one of those units contains 2 N. So we're at 3.83 times 10 to the 22 for C. Which of the following is a decomposition reaction? So that's just something falling apart. Looks like 4 is a decomposition. So 1's a combustion, 2's a combination, 3 is also a combination. So it's only 4. Empirical formula of a substance is given there. The molecular weight is known. What is the molecular formula? So this is just figuring out the mass of this. So carbon's 12.01 times 6, 1.008 times 5, plus 14.01, plus 16 times 2 is 123. So you can see there's 3 units. That works out to be 3. So we got to triple all of these. So C18, H15, and 306. So it would be E. So be careful to look through all of them to make sure they're all correct. Moving on to number 10. Combustion of a sample leads to CH and O. There's the empirical formula. The compound. So what we want to know is, the number of grams of carbon plus the number of grams of hydrogen. We can subtract those off in the sample to get the mass of our third element here of oxygen. So the number of grams of carbon here, 2.265 is the mass of CO2. And then of that, 44.01 grams of CO2, where 12.01 grams is carbon. So I'm just going to multiply by 12.01 divided by 44.01. That's just the percent carbon in CO2. So that's 0.618 grams of carbon, and then the grams of hydrogen in that water, 1.236. Just think, well, the mass percent of hydrogen would be 2.016 grams of hydrogen divided by 18.02 grams of water. So only 0.138 grams of that is the hydrogen. And then the oxygen is our difference. So 1.031 minus 0.618 minus 0.138 gives me 0.275. So the grams of oxygen are equal to 0.275 grams. So we convert these to moles of each of those elements. So the moles of carbon, 0.618 divided by 12.01 would be 0.0515 moles of carbon present in a ratio to 0.138 divided by 1.008. So that's 0.137. Moles of hydrogen present to every 0.275 divided by 16, which is 0.0172 moles of oxygen. So then in terms of a simple whole number ratio, 0.0515 divided by 0.0172 works out to 3. So it's dividing all of these by the smallest, which is the oxygen. 0.137 divided by 0.0172 is 8 moles of H, 7.97, and to 1 mole of O, so C3H8O for A. Compound is 80% carbon, 20% hydrogen. The molecular weight's double the empirical mass. What's the empirical formula of this compound, and what's its name? So, we might say 80 grams of carbon divided by 12.01. That would be 6.66 moles of carbon. If we take 20 grams of hydrogen, we know that's a ratio that would be true. If we have 80 grams of carbon, we should have 20 grams of hydrogen. That would be 19.8 moles of hydrogen. That divided by the smaller is 3. So the ratio here is for every 1 mole of carbon, we have 3 moles of H. And so CH3 is the empirical formula. Can't write all of a sudden. So CH3 is the empirical formula, and there's 2 of these units in the molecular formula, so C2H6, and that's ethane. So empirical CH3, molecular C2H6, name ethane. Which of the following, what are the coefficients respectively when the following reaction is balanced? So we're going to need 3 nitrates, to balance here. We would need 2 here. That's actually going to kick us now up to 6 nitrates. So once we balance the aluminums first, and we put 2 in front of AlNO3, then we have 6 nitrate groups. So I'm going to need 6 in front of NaNO3. So then 3 in front of sodium sulfide gives me 6 sodiums on both sides, and then that should balance the sulfurs, and I have 3 sulfurs on both sides. So 2, 3, 1, 6. 2, 3, 1, 6. Answer D, because we're giving these from left to right across. Sulfur and oxygen react here. We got a gram of each of sulfur and oxygen to produce SO3. What's the percent yield? The key is you don't know the limiting reactant, so why don't we again figure out the number of grams of SO3 that we can make if we consume each of these reactants. So let's calculate this through twice. Number of grams of SO3 that we can make. You can set up a BCA chart if you prefer, but I think this is a simpler and faster way. We just take each of our reactants. So O2 is 32.00 grams per mole O2. For every 3 moles of O2 that react, we produce 2 moles of SO3, and then 1 mole of SO3 contains a molar mass of 32.06 plus 16 times 3, that's 80.06. And then likewise with sulfur, it's about the same as oxygen. It's 32.06 grams per mole of S, but the difference here is for every 2 moles of S that react, we still produce only 2 moles of SO3, and then it's 80.06 grams per mole of SO3. And so the oxygen is probably going to produce less, but sometimes it's helpful to run through the numbers just to make sure. Times 2 divided by 3 times 80.06, I get 1.67 grams of product I get if I consume all the oxygen. If I do this with sulfur, divide by 32.06 times 2 divided by 2 times 80.06, I get a greater quantity, 2.50 grams of the product would be made, but I can't make that much because I run out of the first reactant when I make 1.67 grams. So the max yield here is 1.67 grams. The percent yield, I get 0.8 grams, be 0.80 divided by 1.67 grams times 100%. Whenever you're doing a yield, make sure you divide grams by grams of the same substance. And so 0.8 divided by 1.67 should give me a yield of 48% for D. 1 mole of which substance contains the largest number of atoms. This is actually on an activity this week in a similar format. So we got 18 atoms here. We get 2 times plus 5 times 3, that's 17 here. We get 5 times 3 is 15, 16, 17, 18, 19. We get 19 for B, and only 8 atoms for S8. So a mole of the substance with the most atoms in the formula would contain the most total atoms, so that would be B. A mole of all substances don't have the same number of atoms, they have the same number of particles of whatever that substance is. So we have a mole of S8, we have an Avogadro's number of S8 molecules, and then each S8 contains 8 atoms. So we have 8 times Avogadro's number of atoms. We'd have way more atoms if we had 19 atoms per molecule or unit. Number 15, substance contains CH and N. It's combusted, yields CO2 and water. So this example here is the first one I think I've solved on like a quiz or a tutorial where it hasn't been O, but it doesn't have to be O. It can be anything. So we're just determining the third element by difference. So I still have a mass of a sample combusted containing CH and N, but yields CO2 and water. So all the carbon's still CO2, all the hydrogen's still water. So I'm still trying to figure out from the percent C how many grams of carbon there are. So the grams of carbon in 2.507 grams of CO2 would be multiplying that by 12.01 divided by 44.01, which is the mole percent, or the mass percent of carbon in CO2. So that's 0.684 grams. And the grams of H from the mass of water would be 1.287 times 2 times 1.008 divided by 18.02. So you're just multiplying again the mass of water times the percent H in water. which would be 2.016 divided by 18.02. Okay, and so then that gives us 0.144 grams of hydrogen. And so the grams of N would be our sample mass, 1.084, minus 0.684 minus 0.144 for 2.5 or 0.256 grams of nitrogen. Now notice the problem's not asking for the empirical formula, it's asking for the percent N by mass of the substance. Percent N would just be the grams of N divided by the total sample mass times 100%. So make sure to look for what the problem's actually asking to see what it is we need to do. We actually don't need to go to an empirical formula, we're just giving the percent N here, so it'll be, oops, I did it. 0.256 divided by 1.084. It's and times 100%, so that's 23.6%. So we got N2 and O2 reacting here. So what can we conclude? So let's see, N2s are the black spheres, the gray spheres are the O2. So I got to put an N2 and two O2s together to make an NO2 and then a second NO2. So make my two NO2s, I do it again. So I get two more NO2s, do it again, get two more NO2s, and then I'm left with an N2. So if the reaction proceeds to 100% yield, what molecules would be present in the box after the reaction completes? The answer would be my 6 NO2s that have been produced and that one N2 that's left over. So 6 NO2s and the one left over, N2. Problem like 16, I think, is really exemplary of being able to think of the particle representation of reactions. You could think through it still with a BCA chart or dimensional analysis. Like you could say you have 1, 2, 3, 4 N2s. How many molecules of NO2 can you make? For every one N2, you make 2 NO2s, so that'll give you 8 NO2s. If we consumed all the N, but then we only have 1, 2, 3, 4, 5, 6 O2s. 6 O2s to the products. For every 2 that react, we get 2 products, so we only get 6 NO2s. So this will be the maximum. So you can go through and solve these problems a variety of ways. Just because it's a particle representation doesn't mean you have to solve it as a particle representation. But hopefully you can picture or imagine the considerations of the reaction regardless of the way the problem's being presented. Like 17, which statement is true when we have magnesium nitride and water being mixed together and reacted according to the reaction? So one says one's the limiting, the other's the excess. The other says the other's the limiting, the other's the excess. One says they're both limiting, one says they're both excess. And one says the yield of MgO is limited by the amount of excess reactant present. The amount of yield is related to the amount of limiting reactant that reacts. So this is just nonsense. It's kind of crazy to imagine both being in excess because one of them has to be consumed if the reaction goes to completion. It's possible that they're both present in the stoichiometric quantities. Like if we have precisely 1 mole for every 3 moles of 1 mole of Mg3N2 present for every 3 moles of water present, then they both would be limiting. So this is technically possible. So we can't rule C out. And then one of A and B could also be true. So now we could make a BCA chart here. We can make a particle chart. It'd be kind of tricky to make a particle chart. But probably the easier way to think through this problem is just pick one of them and calculate how much of the other you need to react with it. So let's say the number of grams of water that we need to react with 3.75 grams of Mg3N2. I remember this molar mass from earlier. I don't even know what problem it was, but 100.9 grams of that substance per mole of Mg3N2. And then for 1 mole of Mg3N2 that reacts, we need to have present 3 moles of water. And then 1 mole of water has a mass at 18.02 grams. So we're saying how many moles of Mg3N2 are present. For every 1 mole that's present, we have to triple that for the moles of water that have to be present, and then account for the molar mass of water. So we got 3.75 divided by 100.9 times 3 times 18.02 gives me 2.01 grams of water that we need to react with this quantity of Mg3N2. So in order to make this go to 0 and be the limiting reactant and consumed in the reaction, we have to have present 2.01 grams of water, which we have. We have 3.2 grams of water present. Okay, so we can consume all the Mg3N2 and be left behind with some of the water as the excess reactant. So water is the excess reactant, Mg3N2 is the limiting reactant. Okay, so let's take a look at number 19. Another particle box. We have F2 and Cl2 reacting to form ClF3 as the product. At 100% yield, what statement is true? And so we have an equal number. We're told we have 6 molecules of each. So let's say the black spheres are the F2s. Let's say the gray spheres are the Cl2s. So we're going to need more of the F2 spheres. So we're going to need to take, say, let's do these 3 here together. And let me uncircle this one here. So we don't need that one circled yet. Okay, so we need, if we're going to make 2 ClF3s, so let's do ClF3, ClF3. We need one of the Cls, so that's the gray sphere, and we need the fluorine atoms, 6 of them, to make 2 ClF3s. So we can do that one more time, because I can take the other 3 fluorines and then one of the chlorines and lasso them out. So I'm going to be left behind with 3 Cl2, so I'm going to make 4 ClF3s, and then be left behind with Cl2, Cl2, and Cl2. So I'm going to make 4 molecules of so let's see here, what are the choices? So 3 molecules of Cl2 remain. Oh yes, I can't count. So there are 4 Cl2s left over. So 1, 2, 3, 4. So 4 Cl2s are left over and remain, and all the fluorine is consumed. Answer E. 20. What is the mass of 1 molecule of CO2 but in grams? We know it's 44.01, but that's either AMU per 1 molecule of CO2, or you can think of it as 44.01 grams per mole of CO2. Now, which one helps us solve this problem? Well, they both actually help, because you could say, well, the mass of 1 molecule of CO2 is 44.01 AMU, and so you can take 44.01 AMU as the mass of 1 molecule, and then go to grams and say, well, the number of grams would be equal to 44.01 AMU is the mass of 1 molecule, and then there's an Avogadro's number of AMU in 1 gram. And so then that's going to lead to probably D or E. So let's do maybe even A. So 44.01 divided by 6.022 e to the 23 works out to 7.31 times 10 to the minus 23. Oh, yeah, it's answer C. So it works out to be C. Now, if you chose to start with this here, 44.01 grams per mole, this would still work. What you'd have to do is just say that 1 mole of CO2 contains an Avogadro's number of molecules, and then from there, just multiply that by, this eraser is weird in videos, but then you can multiply by 1 molecule for the mass of just 1 molecule. So it's the same arithmetic that we just did, that you arrive at the same answer, C. So moving on to A, it's a empirical formula problem given percent masses. So you're just going with the atomic weights to moles. Now, so again, what I like to think about in these problems is not necessarily assuming 100 grams and not knowing why I'm assuming that. I just want to assume a ratio of masses I know to be true, 48.6 grams of carbon to 43.2 grams of oxygen to 8.2 grams of hydrogen, and just go to moles of each of these. And so take 48.6, divide by the molar mass of carbon, So that's 4.05 moles of carbon present to 43.2 divided by 16. So that's 2.7 moles of O, and then 8.2 divided by 1.008, that is 8.13. Moles of hydrogen, identify the smallest, divide them all by the smallest. So 4.05 divided by 2.7 gives me 1.5 moles of carbon to 1 mole of O to 8.13 divided by 2.7 to 3 moles of H. So I just start going times 2, 3, 4, finding the first one, so times 2 works. So this is going to be C2, C 1.5 times 2, which is C3, O2, H6. So C3H6O2. Looks like answer E. Then XF3, we don't know what X is, but it's this percent by fluorine by mass. What is the atomic weight of X? We did a problem like this recently on one of the quizzes, but the idea here is that the percent X in the compound would be the atomic weight of X divided by the formula weight of X times 100%. You see how I'm just using the simple idea of what percent by mass means here to write this expression. So this isn't really all that fancy of an expression. But the problem is I don't know either the atomic weight of X or the formula weight of the, it would be actually of the XF3. So the percent of an element in the compound is just, the atomic weight of the element divided by the formula weight of the compound. So I could, though, take the percent F and know that it's 3 times 19.00 AMU divided by the formula weight of XF3 times 100% and know that that's equal to 64.8% as given in the problem. And so then I can get rid of the percent, go to a fraction, solve for the formula weight of XF3, cross multiply, so I divide 3 times 19, 3 times 19.00 divided by 0.648 works out to a formula weight of 87.96. So that gives me a formula weight of 87.96 AMU. Now I could just subtract 3 times 19 and know that's what's X, or I can take this, plug it into the formula weight in the percent X formula and know that the percent by X is just all of the difference. So 100 minus 64.8 is 35.2%. So I can take the formula weight times 0.352. So we do 87.96 times 0.352 gives me 30.96 or 31.0 AMUs. So that would work out to 31.0 AMU in the problem. Okay, so that's a set of solutions to this Chapter 3 set of practice problems. Thank you for the attention.